This is problem 22.8 from Young and Friedman's University Physics book. They give us 3 point charges, all with different charges, and they ask us to find the net electric flux through each of the surfaces they've drawn. They also ask, do your answers in these parts depend on how the charge is distributed over each small sphere? This problem is testing your knowledge of Gauss's law from section 22.3 in their book. Gauss's law states that the total electric flux through a closed surface is proportional to the net electric charge inside the surface. Let's start by considering the closed surface S1 seen in pink. We are asked to find the net electric flux through the surface, thus we want to use Gauss's law equation. Note that epsilon naught is a constant. Now we can plug in our variables into the equation. Surface 1 contains only point Q1, which equals 4 nanocoulombs. Don't forget to convert to appropriate units. We want coulombs, not nanocoulombs. Thus we calculate to be about 4.52 times 10 to the second newtons meters squared per coulomb. Next we're going to consider surface 2, seen in blue. This is very similar to surface 1. It only contains one charge Q2 of negative 7.8 nanocoulombs. Thus we get negative 8.8 times 10 to the second newtons meters squared per coulomb. Now let's look at surface 3, seen in green. The surface 3 contains both Q1 and Q2. To find the net flux of the surface through the surface, we need to calculate the net charge enclosed in the surface, so we add the charges together. We then calculate and get negative 4.29 times 10 to the second newtons meters squared per coulomb. Note that we don't add the absolute value of the charges, so those signs matter. Next, let's see surface 4. It's seen in purple. Surface 4 contains Q1 and Q3. Again, to find the net flux of the surface, we need to calculate the net charge enclosed, so we add the charges together and calculate it to be 7.23 newton meters squared per coulomb. And finally, surface 5 is seen in gold, and it contains all 3 charges. Again, to find the net flux to the surface, we need to calculate the net charge enclosed in the surface, so we add the charges together, paying attention to their signs. We then calculate negative 1.58 times 10 to the second newtons meters squared per coulomb. Let's finally get to that last part of the question. Do your answers in parts A through E depend on how the charge is distributed over each small sphere? Why or why not? The answer is no. Gauss's law equation is only concerned with the amount of charge enclosed in a closed surface, and so the charge can be located anywhere within the volume of space.